Okay, thank you. Thank you for allowing me to talk, and Patty, thank you for forcing me to talk. I was hoping I wouldn't have to, but you twisted my arm successfully. So, cosmology and the probability of Patty. Now, this is a statement that Patty said. I think you might say that at most of your lectures, but it's something that's stuck in my head, and it's been the topic of discussion a lot here, and I probably won't discuss it much because I don't know enough. As Patty has described me, I am not a card-carrying general relativist. But I do cosmobiology, and I claim to know a lot more biology than cosmologists. So I thought I'd talk about this, particularly, now is this going to work? I have to turn it on, I bet, to make it work. Yes. So one thing about biology and physics, when I first went to graduate school in physics, you know, we were proud of ourselves and how much we were learning, and we said to ourselves, all biology depends on chemistry, and all chemistry depends on physics, so physics is the most fundamental kind of science. So I went home on vacation, and I talked to my dad about this. I said, hey, look at physics, we're good. And he was a high school biology teacher, and he said to me, but all physicists are biologically evolved creatures. So all physics depends on biology. And I scratched my head and I said, there's a certain amount of wisdom in that. So anyway, biology has played a role in the things that I think are important about the universe. And I've noticed that nobody has mentioned biology, but this conference so far has been a bunch of biologically evolved critters talking about non-biology. So I thought I'd add a little biology to the works. Now, I've also been asked about planets. Now, in 2012, we had this plot. Now, this is the period of a planet, an exoplanet. These are planets around other stars. And here are the masses of the planets. Here is the Earth, and here's Venus, Mercury, Mars, Jupiter, Saturn, Uranus, Neptune. So there's our planetary system. Here's the different techniques we have used to find these exoplanets. And notice that the Kepler ones dominate here. If you go back about before Kepler, then you would be dominated by the radial velocity detections, which are here. And you notice that they're all up here. And that's a selection effect, because it's very hard to detect things that are either very far away or have longer periods. So very far away is right out here. Now, except for the direct detections, which need to have a planet very far away, but they have to be very young in order to detect. Now, 3 years later, this is what the plot looks like. So you can see this red cloud turned into a red blob, and it's slowly moving over here, and then the gyroscopes broke. And then Kepler program had to stop, and then it had to start moving around and looking somewhere else. But the whole point here is this blob was moving, 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 and there started to be planets here, and that makes news because then you find Earth-like planets, and Earth-like planets means Earth-like life, and Earth-like life means, I don't know, aliens, Mr. Spock, and other things. Okay, so that's the progress that has been made. It's enormous progress. It's continuing, and over the next decade, we're expecting to see lots and lots and lots of more points here. Now, I've also been asked about the Trappist system. First of all, because of the statistical analysis you can do on this, the new default is that every star you look at has some type of planetary system around it. Put that into the back of your heads. Whenever you see a star, think it's probably got we're pretty sure it's got some type of planetary system around it. We weren't sure of that. Some theoretical people kind of waved their hands, but now we're very sure of that. And so use that as your default. And what that default looks like is something like this. I don't know if you can see that, but every single one of these stars has some type of very faint white. You can't see it, so let's move on. Now, the Trappist system. So this came out about a week or two ago. And so now, notice the word, first of all, it's 7 planets. Here is the star. These dots are the 7 planets. And the gray here is the habitable zone, circumstellar habitable zone. And here are the photometry, where you have these dips whenever it passes in front of the star. So it's a system that's aligned, so you can get these dips. And what I wanted to say about this is, first of all, there are 2 types of habitable zones from here to here, or a little bit larger, depending on what you consider to be the habitable zone. And the sun, here in the middle, has 8% the mass of the sun. Now, that is about as low in mass as you can get and still call yourself a star. So the transition between a brown dwarf is about 70 Jupiter masses, and this is about 80 or 83 Jupiter masses. So it's very, very tiny, very, very low mass star. And that's interesting, but it also produces a luminosity that's 5 times 10 to the minus 4 of the luminosity of the sun. But when you have such a low mass star, a big problem is the planetary habitability because of the long pre-main sequence Hayashi track. So here's the main sequence in an HR diagram. Here's the sun here, and you can see all these stars going onto the main sequence. Now what happens for a very low mass star is that the Hayashi tracks are almost vertical, which means that the luminosity just goes down, 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 down. And you can see this is 2 orders of magnitude here, from here to here. And that's about, now the star, the Trappist host star is about right here. Right? So instead of 0.1, it's 0.08. So it's about right here. That means this path here is about probably 500 million years, maybe even more than 500 million, close to 1 billion. So for 1 billion years, pre-main sequence, that luminosity of that host star has been decreasing by 2, at least 1, maybe even 2 orders of magnitude. That means that if you were a nice planet in the current habitable zone, you were being incredibly illuminated, and you probably lost all of your volatiles if you're a planet the size of the Earth. Now, you notice that the moon, our moon, is in the habitable zone, but it's not habitable because it's not big enough to hold on to something. Our Earth has an atmosphere because it's big. Now, these planets are big. They could hold on to something, except if they were irradiated for 1 billion years by 10 times the luminosity, which they are now having. So the idea of, hey, habitable planets is a little bit of an exaggeration that is worthy of newspapers. They didn't mention this in the paper until the last line. If you look at this Guillaume paper, they'll say, oh, by the way, there are some problems with this. And then they listed 3 or 4, which are major problems, only one of which I'm telling you here. So that's some of the details of this. But it's incredible. Why it's so incredible is because we found a 7-planet system. That's hard to find. I think there are only 1 or 2 other 7-planet systems in the Kepler data. And it tells us a lot about how planets jostle each other around. And, well, here's the luminosity histogram of stars. Here's the sun. And you notice that the sun is quite unusual. 95% of stars are less massive and less luminous than the sun. And the one that we're talking about here is probably off the plot right about here. So the bottom line is 500 million years of host luminosities, that is 10 to 100 times larger than the main sequence luminosity used to compute the current habitable zone. That's a problem. Okay? But anybody have any questions, just interrupt and just call out. Any questions? Yes? This is a slightly supersolar metallicity, so I think it's its metallicity is 0.4, 0.04 or 0.4. I've forgotten. Anyway, it's slightly supersolar in metallicity, and it's not strongly dependent on that. So if you had one you varied in luminosity, varied in metallicity by, I don't know, 0.1, 0.2, 0.3 dex, the luminosity probably wouldn't change. It's the mass mostly. Okay. Now, here's another paper we wrote recently, The Case for the Gaian Bottleneck, the Biology of Habitability. And the context for this is that a bunch of astrophysicists are computing habitable zones. And they are ignoring life. And it might just be that life plays a larger role in maintaining the habitability of a planet than the luminosity of a host star and the distance from that host star does. So life has that way of doing it. For example, your body temperatures are 37. They're kept that way. The temperature goes down by 5 degrees, goes up by 5 degrees. You still stay at 37. And so that type of regulation might be produced by the biosphere itself. This is like the Gaian hypothesis. So this is why it's called the case for the Gaian bottleneck. So now, when you have a planet, you have certain amount of positive and negative feedbacks. On the left, these are positive feedbacks. So the surface temperature goes up. You then get less ice cover. That means you change your albedo, and then that makes the thing go up again. So you either go this way or this way. The whole point is that this is a positive feedback. The same here with volatilization, runaway greenhouse, and then you get hotter and hotter and hotter. So on the left-hand sides are 2 mechanisms which produce, you get a little hotter, then it gets really hot. Then it gets really hot, then it's getting even hotter. That's positive feedback. On the right, we have negative feedbacks, and that's like a thermostat. That's what you want if you want to maintain habitability. In 1981, J.R.R. Walker came up with a method to regulate the surface of the planet, the temperature of the planet, with an abiotic mechanism. And this abiotic mechanism, this is the paper, is called silicate weathering. where you have weathering and then you pull down the CO2. When you heat it up, you get more weathering, pull down more CO2, and that reduces the surface temperature. That requires surface rock. Now, if you talk to an Earth scientist and ask them, when did this Earth get continents? When did they have rocks above the surface of the ocean? They'll say, oh, maybe 3 billion years ago. So notice the Earth is 4.567 billion, so that's like a billion or 2 years, a billion or 2 years in which there was not a lot or even any continental crust in order to make this process work. Now, that's important because this process has been invoked to produce the habitable zone. You say, well, how wide is the habitable zone? That depends on how strong this negative feedback is. If it's really strong, then it's very wide. If it's non-existent, then it's also non-existent, the habitable zone. So over here we have runaway greenhouse, runaway glaciation, which everybody is convinced of. But over here we have stability if these things are working. All right, so this is a picture of it. Most people think, okay, over here's runaway greenhouse, too hot. Here, runaway glaciation, too cold. And then the width of the habitable zone depends on the strength of the negative feedback. Now, we're suggesting that maybe that negative feedback does not exist. If that's the case, you have the habitable zone looks more like this. You don't have a habitable zone. You're up here and you fall down this way or you fall down that way, and that's the default. So you have no silicate weathering the first billion years, so no negative feedback, and so essentially no habitable zone. You heard it first here. So cars don't stay on the road without a driver. Maybe planets don't remain habitable without life. So this is a plot that we put into this paper. Up in the top, so here's the time from the beginning of the solar system to today. And here's the accretion rate. So boom, 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 the Earth's accrete gets bigger and bigger and bigger. And when you integrate this curve, you get the mass of the Earth today. Here's the Earth today. Now, here's the distance from the star, and here are a couple of plots of habitable zones. In 1979, before the 1981 paper I mentioned, Hart calculated the continuous habitable zone, and this is what he got. A number between like 0.95 and 1.01. And I think that's kind of a ridiculous calculation because, you know, you knew what the answer had to be. We're going to put Earth in a cap. Now, what kind of mathematical shenanigans can I make such that Earth stays in this tiny habitable zone? But he didn't have this abiotic negative feedback. And then along came the negative feedback, and then ever since then, you've seen habitable zones that are gigantic because that's been assumed that you have this silicate weathering early on, and we're suggesting that maybe you don't. If that's the case, then what you have is, this is like the mean surface temperature. In the beginning, because of this high accretion rate, boom, boom, freezing hot, you get things that go up and up and up and down, and then you get the runaway greenhouse, or you get the runaway ice albedo, and then, if perchance life figures out how to control some of the gases, like the oxygen in the air right now, for example, that you're breathing, then you might be able to learn how to regulate that. And if you learn how to regulate that, well, maybe that prevents you from falling off to one side or the other. That's not assured. Maybe it's some kind of weird, quirky evolutionary thing that produce something that doesn't happen very often. We're not quite sure. But anyway, here's the Earth, up and down, kind of Gaian regulation going on here, and then the sun gets too hot, and then boom, we all die in about 1 billion years or so because we lose the water. That's something that even life can't, you can only use an air conditioner so much. If it gets really hot, the air conditioner breaks down, and that's probably what's going to happen here when we lose the water on the Earth. Okay, so here's the planet, here's the inhabitant, and then extinction. The default for planetary life in the universe is a hypothesis that we are proposing here, and I think it's consistent with all the data, and it might be something that we should take more seriously. All right, so any questions on this, by the way? Yes?
Is there also this channel for the carbon monoxide to get locked into bicarbonates, or is that not very likely to?
Carbon monoxide, that's tricky. It depends on how much carbon monoxide you have around and what the earliest...
Sorry, carbon dioxide.
Oh, carbon dioxide.
Sorry, yes.
So carbon dioxide to get what?
Into bicarbonates, and then you have something else in your surface.
Well, that's what this is. That's what the silicate weathering is all about. Okay, that's what the silicate weathering. That's if you're interested, 1981, the Walker paper. Okay, so this is a plot I made a long time ago, and this is saying, okay, we have an Earth. How does our Earth compare to other Earths? Well, here's the star formation rate. Here's today. Here's the Big Bang. And the star formation rate, we look at, oh, it goes up and up and up and up, and then it's got to come down to 0. And so that's approximately the star formation rate. It's kind of like the Medal plot. All of these stars are producing metals, and so the metals in the universe are going up and up and up and up, and that's what this is. To get a rocky planet, you need somewhere in the neighborhood of 1/10 of the solar metallicity. And so it only gets up to there, about here. And so this distribution of Earths is kind of like the distribution of the stars, except with the front end cut off, where these earliest stars do not have enough metallicity to produce the silicate rocks that we are living on now. So there's been plenty of time for life to have evolved elsewhere. So here's where we evolved. Here are the young Earths, and here are the older Earths, about 3/4 of them over here. And this is why Stephen Hawking says, I think we should keep our head down. We shouldn't broadcast our existence with radio tells us, hey, we're over here. He thinks we should listen, but not talk. And the reason he thinks that is because, on average, these guys have had about 2 billion years longer than we have to evolve. And 2 billion years is a long time. Ask a biologist. But 2 billion years ago, our ancestors were amoebas, single-celled, probably eukaryotes. But they weren't building radio telescopes or atomic weapons. Now, if life is common in the universe, as suggested by the rapid appearance of life on Earth, then this age distribution, this one here, gives us an idea of how we compare to other life that may exist in the universe. And just for those who are interested, just recently, this Nutman et al. Paper said, hey, earliest life, 3.75, based on stromatolites, isotopic evidence the year earlier, up back to 4.1, and a new paper 2 weeks ago said, well, we have looks like some microfossils from older than 3.7 and younger than about 4.28, I think. So we astrobiologists are really aware of all these dates here because we're trying to figure out when was the first time life emerged on Earth. Any questions?
When will be the first time that intelligent life occurs on Earth?
Okay. So now you used the word intelligence as, I guess, is this a one-dimensional thing for you? Anyway, we could talk about intelligence for a long time. It's an n-dimensional quality, and that's hard to talk about. Okay, next. So here's a Hollywood alien, and here's a Bollywood alien. Now, when you look at movies or read comic books, they look like, here's the good aliens, and then here are the bad aliens, and we astrobiologists who are looking for life elsewhere kind of think of this as superstition and say, well, if this is superstition, what is the reality? So the reality, as far as we can tell, is based on the phylogenetic trees that we can create out of very conserved genes. The one on the left is an older one based on 16S, the ribosomes inside your body, every cell. And so they're bacteria, archaea, and eukaryotes. And the aliens, here, by the way, is Homo. This is all animals are right there. And here's Caprinus, fungi, and here plants right there. So those are the aliens, because notice that the aliens were all animals, right? And so the aliens, if you had to classify aliens as what kind of life form, they would be right here. Now, this is old. This is about 20 years old. But this is a new one that just came out. And, I wanted to say, you know, probably when you're in high school, it said, there are two types of life forms. There's prokaryotes and there's eukaryotes. And then Woese, about 1980, discovered the archaea. So there became, from 2 domains, turned into 3 domains, bacteria, archaea, and eukarya. But then we figured out that the eukaryotes don't branch separately, they branch inside of the archaea. So it became 2 domains again. But then a new paper said, well, wait a minute, there's a bacteria, but then there's a new branch, a new group of bacteria, and here are the eukaryotes here inside of the archaea. So we've made lots of progress in biology. We've gone 2 domains, turned into 3 domains, turned into 2 domains, turned into 3 domains again.
Where are the viruses?
The viruses are not here because these are based on ribosomes, and viruses don't have ribosomes. That's a good question. I should say non-viral life. In other images, I say non-viral tree of life. Okay, you could also say, where are the convection cells? Where are the hurricanes? Okay, so just a little bit of there's a group called epistoconts, that means animals and fungi, and that is this little dark line here in this new tree. So all of the aliens that you've ever seen on television belong to right there in this tree. And you might imagine that we are making aliens like ourselves. Okay, so 4.5 billion years ago, this is what the sun looked like, and then it turned into this. And we astrobiologists would like to know how often this type of transition occurred. So we have a cold, odorless gas turning into a kangaroo made out of carbon, oxygen, hydrogen, and nitrogen. And that brings me to this topic. How did something like Paddy ever come into the universe? It's a little like how did something like a kangaroo ever come into the universe, but we're talking about Paddy here. So let's talk about Paddy. Now, what is the probability of Paddy sitting there? He's sitting there thinking something, and like any human being, but let's call it, as the probability is epsilon. And let's make epsilon as small as you'd like. Oh, it's very improbable to have a Paddy, so 10 to the minus 10, 10 to the minus 20, 10 to the minus 157,000, whatever, it's small. But we have current observations are consistent with the universe being spatially infinite. This is not the particle horizon, but this is the entire universe. So I learned from my mathematical friends that if you multiply epsilon times infinity, you get infinity, which means that there are an infinite number of Paddys in the universe if his probability is epsilon. On the other hand, is Paddy a set of measure 0? And I have a hard time with the set of measure 0. Usually I'm told, okay, if you embed the rational numbers inside the real numbers in an interval of 0 to 1, then you have an infinitely sharp knife and you go like this. The probability of landing on a rational number is 0, even though they're an infinite number between 0 and 1. And that's kind of like the definition of set of measure 0 I have in my head. But I'm trying to understand, is a set of measure 0 associated with Paddy something that makes any sense? And I said, well, let's simplify it. Let's do a paddification of this problem and say, let's consider only an electron. Consider an electron. And somehow this is an electron. Here's the wave function of the electron. And then it has some type of peak. We use real numbers in Hilbert space to talk about this peak. And I think that the point of maximum here is at it is an exact number. And here's the exact number. It goes on forever. And if that's the case, then the position of that electron is a set of measure 0. If these digits go on for an infinite amount of longer and longer and longer. And then you say, well, wait a minute, what about the Heisenberg uncertainty principle? We physicists are empirical. We do not like talking about delta x's that get infinitely small. On the other hand, are we really, is that just an empirical result, and do we have an ontological reality, a little philosophical talk, the reality independent of you measuring it? This is like saying, is it possible that an electron has an infinitely precise precision to its position when you don't look? And I don't know if we can answer that question, but it's possible. And if that's possible, then this electron being at that exact position has a set of measure 0 probability. And if that's the case, then sure, you've got lots of electrons in you, so you could be a set of measure 0. Paddy, you react to this, please.
I'm very glad you allowed me my existence.
I'm trying to figure out what your probability is. I know you exist. The question is, how many of you are there in an infinite universe? And then there's this idea of, wait a minute,
Parenthetical comment.
Go, please.
Yeah, which is also related to your comment about this 2 billion years aliens had existed. What astrobiologists also ignore is the sociology of the alien. If the aliens have a neurochemical process very similar to human beings, as far as human beings are concerned, I am absolutely certain that we are going to blow ourselves out in 1500 years from now, or make the environment so bad.
1,500. Wait, Trump is going to have 4 years. It's going to be 1,500. Come on.
At least 1500. So which means that the lifespan of a civilization after they discover plastic
Yes.
or atomic fission
Yes.
is about 2000 years. So the chances that we are ever going to come in contact with them is negligible.
Yes, this is.
They won't blow themselves out. That is one reason nobody might ever contain gravity.
Well, what you've just described is called the self-destruction solution to the Fermi's paradox. Fermi's paradox is, hey, if there's planets everywhere, there's water everywhere, rocky planets everywhere, and let's suppose that if life will form there, and then life turns into technological life, and then they make radio telescopes, but where are they? We've listened for a while now, half a century or so. We've got Matter of fact, the SETI searches got a boost of $100 million a couple of years ago. We're getting better and better at looking for alien signals. And yet we haven't found any. And so what's the answer to that? You've just suggested self-destruction, lifetime. Now, you agree with Frank Drake. Frank Drake has a license plate that says N equals L. N is the number of communicable civilizations that we can talk to. And then there's some terms, but the most important term, as you suggest, and Frank Drake agrees with you, is L, the lifetime of the civilization. If the lifetime is very, very long, billions of years, we're going to be a lot. If it's only, a couple of thousand years, then forget it. So you agree with Frank. I disagree with that because I think that human-like intelligence is not a convergent feature of evolution, and we should not expect. But not only is it possible, the data points to that, and the data being Australia, New Zealand, South America, Madagascar. These are independent experiments in vertebrate evolution, which has not shown any indication of vertebrates wanting to have big brains like us and start playing around with computers.
So they may not discover atomic fission, and then they are safe.
I wouldn't say they're safe. They're going to go the way of every life form when their sun, as you build up the hydrogen ash in this core, the sun gets higher, and then if you're in the habitable zone to begin with, you start losing the water, and then. That's right. It won't be self-destructive. Well, of course, it depends on what you mean by self. Okay, so I'm almost out of time, but I did want to say, there's this caveat. Well, wait a minute. What about the Planck length? If I take 0 to 1 and I'm putting an electron into an exact position, am I forgetting about the Planck length here? And I don't really understand the Planck length well enough to know whether if you put a grid of the Planck length on this 0 to 1 interval and say, oh, this electron has to be either here or here or here or here, well, then you have not a set of measure 0, but you have a large number of Planck lengths between 0 and 1, but you still have non-infinite. If that's the case, then you're not a set of measure 0, and then there's an infinite number of you in the universe, I think. But then I'm thinking, well, you know what? If I have a grid here, that's the grid, but there's nothing about this Planck length that says, why couldn't I rotate the grid a little bit or move it a little bit? I don't know if that's possible, but it seems to me if you have a grid like this, you cannot have a discrete number of places you can be if you allow this grid to move around by tiny amounts that are less than the Planck length. I don't know if that's possible or not. Do you know if that's possible or not? Can you?
Yeah, the way Planck length comes as a 0-point length is not like a grid at all.
Right. If that's not like a grid.
It is like existence of molecules at finite points in a gas. They are not grid. It is not like solid. It is more like gas. We can talk about that.
So it's legitimate to think of this electron having a. Oh, good. Well, then you could be the only party in the universe. All right. And then I wanted to say, so one question that we astrobiologists are always asking ourselves is the complexity of the universe increasing? If you study biology, you say, oh, yes, it gets more and more complicated, and we're really complicated. And to address this question, we put the book together, Complexity in the Arrow of Time. And I think the short answer is, I think astronomers in particular, and biologists in particular, when they talk about the increasing complexity, they are looking at what I call the 1%. Now, if you look at America and say, okay, the 1%, are they getting richer? Yes, they're getting richer. But if you ask, is America getting richer? The answer might be no. 99% is getting poor, and the 1% is getting richer. So if you look at the most complex thing, or the most rich people, the richest people, then you get the impression, oh, the richer people are getting richer and richer. So I think, however, when you do that, you're doing it at the expense of the other people. And that might be the case in the universe. And I want to thank you, Patty, for your sense of humor, your cheerful civility, and your deep physical and mathematical insights. And as a birthday present, I put this book inside your bag. You saw that. Oh, it wasn't a surprise. Oh, all right. Anyway, thank you very much.
Hello. I've just got two quick ones. Firstly, so the late Stephen Jay Gould used to say often that if you ran the life experiment again on Earth, there's absolutely no guarantee that you would end up not just with the same answer in detail, but even remotely the same answer. Do you have any comment on that and how it affects some of the extra extraterrestrial things you alluded
Yeah,
to.
yeah, that's probably one of the deepest questions in astrobiology. And Stephen Jay Gould is on one side, a guy named Simon Conway Morris is on the other. Simon Conway Morris is he wrote the Bible of Convergence. The idea is, and plus the replaying the tape of life thought experiment, they usually start at the Cambrian explosion about 540 million years ago. They don't go all the way back to the beginning. I think if they go back to the beginning, you will have even less similarity to what we have. And so I tend to agree with Stephen Jay Gould, but I think we need to address also the issues that Simon Conway Morris has brought up. And that is, you know, he lists examples of convergence. And the simplest example of convergence is, hey, you ever see the way the hydrodynamic way a shark is and a dolphin? Look at how similar they were. They had common ancestors which didn't share that, but you got a body about this big and you want to move through this liquid. Well, there's certain physical things that reduce the drag, and that's what has happened. So that's convergence. On the other hand, if you look at the genomes that were responsible for that convergence, the only similarity I think you will find is in the genes that were shared by the common ancestor of the dolphin and the shark. That was about 380 million years ago. Okay? So there's a lot of... so whenever I talk to Simon Conway Morris, I talk deep homology, deep homology, deep homology. That is, all these things that you're saying have converged, they have been identical up to very recently. For example, he uses saber-tooth tigers and saber-tooth the thylacosine in Australia. But they had a common ancestor about 180 million years ago, and that common ancestor had the ability of just a few genes to turn up and down and control the growth and size of things during embryogenesis, where the size of things are mostly determined. So every time he says it's convergence, I said, that's deep homology. It's convergence. It's deep homology. So we're trying to, that's the nature of the controversy. It's important because if we can figure out what has happened independently here a couple of times, then that becomes a good candidate for what we should expect elsewhere. But that independence is, for our biologists, they really don't know what the word independence means. And so it's really tough. And I guess you have to point out again and again and again that here's the origin of life. Here is this, up until the common ancestor of the thylacosine and the saber-toothed tiger. And then the tiny, tiny little divergence. And he's claiming that the saber teeth evolved independently. I think that's crazy because they're just not looking carefully at the deep homology, the shared genes of the common ancestor. So I'm a little bit on the Stephen Jay Gould side of that argument.
And the other thing, just quickly, and this goes to Paddy's point about self-destruction, this whole story on Earth started through chemical evolution, supposedly. I mean, of course we don't know, but there were chemicals, they were competing for resources in their reactions, they developed membranes, blah, blah, blah. Why would that not all happen again, even if we do self-destruct? Why do we just see it as a one-shot process when we're talking about things like the Fermi paradox? Surely these deep chemical imperatives would play themselves out again, but just in a different form even after we're gone.
Right. Well, you may notice that when we say word we, it could mean we humans that are doing this technology and are presumably going to be responsible for the self-destruction, or we can say we, the life forms of Earth. Now, when Paddy says self-destruction, he doesn't mean self in the sense of all life on Earth. He probably means we human beings and maybe almost all the animals, because they're kind of similar to us and they would be destroyed when we kill ourselves. So that does not bring us back to the origin of life. It essentially wipes out everything that's evolved in the last billion years or so. It brings us back a billion years, and then we can go on from there. So you will not have a new beginning at all at the stage that you described of chemicals trying to figure out if they're alive or not. So any
conditions will be completely different after the self-destruction.
Yes, they're going to be there are lots of bacteria that will learn how to enjoy all the radioactivity that we produce, for example.
Okay, I have one comment and two quick questions. So one is the comment is for what Paddy said. I guess in some of the inflationary models, the ever-inflating universe, we can have Googleplex universe, which we can have infinite number of Paddies. And
what cardinality of that infinity? Do you have any idea about that? What's the cardinality of the multiverse?
It's
countable, or
either in many words interpretation or a multiverse, we can have most infinite number of Paddies. So it's good to have infinite number of Paddies, anyways. So the questions are whether we are only looking for life which is carbon-based, or we can look for other form of life. And the thing is it because of us, which are human beings, we are very self-centered, that we think we should be worried about extinction? You know, big dinosaurs were here for more than 350 million years. Where are they now? And we have been here less than 2 million years, I mean, or maybe less than that. Why we should think that we're going to be here for forever?
Right. Okay, so first of all, when you say looking for life, the only reasonable chances of looking for life now are the SETI searches. And there you're not looking for carbon-based life, you're looking for any kind of based life that can produce radio signals and radio telescopes, right? So there's not that type of chemical bias there.
Maybe the technology would be sent in gravitational waves or something.
Right, sure. And in about 10 years we'll be able to listen to them. And we'll make a giant discovery of, and so Jodie Foster should study gravitational waves rather than radio waves. Okay. What was the second part of the question? Oh, so how biased are we in our search for life elsewhere? Well, the next step over the 10 to 20 years will be looking for chemical disequilibrium in these rocky planet atmospheres. And so we will try to get as best a hold we can on looking at the composition of those atmospheres and whether there's any signal that says, hey, there's life. Now, it's interesting because life produces disequilibrium, but it also undoes it. So it's a complicated thing, and we're working on that from both, well, theoretically trying to figure out how do you quantify exactly chemical disequilibrium. This is like the Lovelock criteria that he published in Nature in 1965. And that's not easy. We're working on it. And you could say, well, the specific type of chemical equilibrium that your instruments have been made to look for could be kind of biased towards the kind of disequilibrium that water-based or carbon-based life would produce. That's an example of some type of bias. But when I talk to people and they say, oh, you could have silicon-based life. Well, the cosmic abundance of carbon is about 15 times higher than the cosmic abundance of silicon. So let's suppose that equal probability of silicon-based life and carbon-based life, well, then you'd have 15 carbon-based life forms for every one of silicon. And
It should be true because Hollywood movies are making those kind of things.
well, good. I'm not quite sure that's any. You can evaluate truth based on that. But just the cosmic abundance we do know about. And carbon is something that we astrobiologists think is probably the best bet. And we're willing to entertain silicon, but so far it doesn't look like a great bet. But even if it were, it would only be equal probability, and then we'd have more carbon-based life anyway. So.
All right. Maybe we'll. Okay.
I'll be quick, Charlie. For better or worse, the Entropic Principle has not been mentioned yet in this meeting.
Yes. Right.
You know, some distinguished cosmologists like to factor it into explaining, for example, the cosmological parameters we observe. So
Yes.
as a cosmobiologist, what's your take on the Entropic Principle?
Well, I guess I'm a good friend of the Entropic Principle, but I don't know enough high-energy astrophysics or string theory to talk about the legitimacy of multiverse. I wave my hands and say, hey, our understanding of the origin of the universe is not just based on GR, it has to be based on quantum. If you're doing quantum mechanics, you're going to have to involve statistics, not unique events. If it's statistics, that suggests that there are these other universes. I'm fine with that. What I'm not fine with is, in these other universes, these constants will change. When I talk to somebody about this, I say, how do you know they change? They say, well, is there any suggestion that these constants change? And they say, no, but it's kind of fun to play with. And so I say, what's the distribution? We don't know, we have no idea. And as long as they have no idea about the distributions from which these constants are pulled in these other universes, I'm content to say, maybe they can't change in that way. If they can't change in that way, then there's nothing to talk about in terms of fine-tuning. Entropic principle is usually invoked to say, there are all these other universes, all these other constants, and only in the universes where they have the correct ones for life are we in, and that explains the fine-tuning. But the fine-tuning problem doesn't even exist unless you think you have these distributions, which I don't think are suggested by, as far as I understand, the multiverse, the theories that create the multiverse.
Okay, let's thank Charlie again. Our next speaker is Professor Anthony Redhead. He'll be talking about a possible powerful new gravitational lensing probe.